Hey everyone, I'm Prasad, student of IIIT Sri City, doing an MTech in IoT and autonomous systems. As part of my first sem deliverables, I'm doing a project called Guardian Tracker. Guardian Tracker is an intelligent safety device which uses LoraWAN network for asset monitoring. It employs CPS approach, which is hosted on GCP, where a machine learning engine predicts battery time to failure and autonomously reconfigures the edge node to extend operational lifespan. Currently in the market, there are a lot of static timers which leads to premature battery drain. The Guardian Tracker provides a predictive CPS loop that dynamically optimizes the energy using ML-driven recommendations, achieving a major performance improvement. It shifts between high fidelity fast mode to low power save slow mode based on ML recommendations. Smartly manages the battery drain. It uses MQTT to decouple sensor from the cloud layer. What you see here on the screen is LilyGo TV version 1.1. We also see a SenseCap M2 gateway, LoraWAN gateway, which provides a backhaul connectivity for TTN. Firmware is coded in C++, connecting to Things network and MQTT brokers to achieve asynchronous communication. Cloud backend is coded using Python Flask on GCP. Data logging is done via SQLite DB. ML engine is used using scikit-learn, a random forest specifically for time to failure analysis. We also do analytics on Jupyter Notebook, and we use TTN console for a low level packet inception and manual downlink control. So I have implemented IoT level 2 topology, where the sensing is node is a lightweight and intelligence is offloaded to the cloud. So this is how the IoT level architecture looks like, where the TBM talks to gateway through MQ and directly goes to database. So from there, the database data is read through ML code, and the actuation happens. So let's get into details. This is a I've divided into multiple phases for easier understanding. So this is the phase one, where the TBM sends data to the gateway to the webhook, through the webhook MQTT broker and to database, and through the via ML engine. Now, this is the ingestion phase. Now what happens in the actuation phase? So ML engine reads the data, understands it and predicts time to failure, then sends the actuation command back to TTN gateway if needed, then back to TBIM. So this is how the actuation looks like. Then comes the acknowledgement phase. That TBIM says, okay, I have actuated and I'm sending the data back to you, acknowledgement back to database through the same flow which the payload takes in, but at a different port 99. Okay, this is the developer environment which I'm working on, and you can see I've connected my T-beam to the serial port, and this is what you see. Just sent a data uplink. First, what happens is it checks for the GPS fix. If it is available, if it is not available, it waits for some time, and then okay, it's failed. Now let's go back. It's going to picks it up, picks up the Wi-Fi. So it's found 12 networks in the Wi-Fi, and it sent the 5 closest ones. And this is the payload, which it looks. And the FC count is 537, and it sends across to the TTN. Let's see how it looks in TTN. And this is 537, right? So let's go and check here. This is a 537 which you're looking at. So this is a 537, and here you see the port 7, it is sent the data. Then this is the 5 Wi-Fi data which is sent across, and this is getting uploaded to the cloud. So let's go and look at the cloud now. So I connect to GCP, and I've set up everything in GCP, and this is where you see the cloud data. Let's see how the logs look. Okay, so what was sent 5:37, and now it looks like the 5:38 has already gone, and so because it is the fast mode, it is done every 1 minute. So you see the 5:37 it's gone in, and 5:38 has also come in, and then you can see the predicted time to failure from the ML program. And yeah, that's about it here, and let's see how it looks in the database. um, so I have listed the last five which I've uploaded, which the uplink has completed. So this is 534, 535, 536, 537. So this is what you see, and you see the battery percentages as well, battery voltage, not percentage, sorry. um, and let's see what the actuation says. So this is the actuation table. So what happens is, you see, when the TT predicted time is lower than the threshold or above the threshold, there are two places. One is fast mode and one is slow mode. So when it's above what where we are happy with the battery percentage, we send the send a command to actuate as a change it to fast mode. That means it sends it. This is all can be configured. So it's now it sends it every 1 minute. So when the ML predicts that it's below the threshold, it sends a command to slow down. So that's where you got the confirmation back from the T-beam. You send a message, T-beam acknowledges saying it's confirmed. So this is one way ML is doing one through this. Another way we can do is through TTN. So let's see how it looks in TTN. So you can schedule a downlink or an uplink using this. So you send it in the port 10, and depending on what you want to do, either upload fast fast in the uplinks or slow down. So depending on that, you send the payload. So the payload right now for us is to set it to fast it is 400, and to set it to slow is 401. Is that's what we are going by. Okay, before we conclude, I want to I have done some analysis of the data which I have obtained, and around 7,000 data points. Um, so this is the feature importance which is shown by as per the ML program. Battery voltage is the only one which is being considered for decision making for actuation, and this is over a lifetime of it's shown how many actuations have happened and how many are pending. The pending ones are because of the code incorrect, and I have fixed the code, and that's where you see that everything else is actuated, and see the green are recovery modes. um, and I have done a analysis on the battery saved. So you can see the amount of battery spent on in 1 hour and in a slow mode and the fast mode. So you can see a graphical view itself. It shows the amount of savings which has been done, and it's like 2.1 times we have saved. And going ahead, geospatial analysis. I have given a reference point as to where it should calculate from, and I've cleaned up all the other unwanted, um, say, zeros and the repeated ones, and which is not doesn't make sense. So I have given a default values in the code, so that's also been cleaned up. And this is where what I've got from the TB, uh, the actual good data. And I've got a displacement of around 638 638 meters. So from the 7,000 data points. So this concludes my analysis. Thank you. To conclude, the Guardian project successfully employs machine learning to optimize the battery life. Our goal was to create intelligent tracker that manages itself, and we achieved those goals. It predicts the battery's failure time and triggers an automatic reconfiguration of the device. So this compared to static, which just uses fixed timers, we are using smart timer, smart way of doing things, and we have achieved a significant 2.1 times improvement in the energy efficiency, and that is shown in this graph which you're seeing. In short, we built a self-managing IoT device which uses ML to predict the battery failure and saves power, thereby lasting 2.1 times longer. Thank you.